Forget everything you thought you knew about black holes. There might be something even more bizarre and mysterious lurking in the depths of space. We are talking about objects that don't shine, don't burn, and defy our basic understanding of stars. Scientists call them exotic stars, and they exist more in theory than in direct observation. Some are so strange they feel like something from science fiction. Recently, physicists have proposed an even more incredible version, a star that can be layered inside another, and then another, like a cosmic nesting doll. They have a name for these too: Nestars. What makes them so compelling is not just their peculiar structure, but what they could tell us about the universe. If these objects are real, they might solve one of the greatest puzzles in modern science: why the universe is expanding at an ever-increasing rate, a phenomenon driven by what we call dark energy. So, are the dark centers of galaxies truly black holes, or could they be concealing something far more unusual? To grasp why scientists are considering ideas like Gravastars and Nestars, we need to start with the fundamentals of a normal star. Stars, at first glance, seem impossible. They are colossal spheres of gas, millions of times larger than Earth, yet they do not implode under their own immense gravity. Why is that? Let's use our Sun as a familiar example. The Sun is essentially a gigantic nuclear furnace. In its core, hydrogen atoms are continuously fused together, creating helium and releasing a tremendous amount of energy. This energy is not just light, it also creates an outward pressure. Every second, photons generated deep within the Sun push outward as they travel through its dense layers, a journey that can take thousands to millions of years. Eventually, they escape as sunlight. This outward pressure perfectly balances the inward crush of gravity. It's a cosmic standoff. Gravity wants to compress the Sun into a tiny ball, but radiation pressure pushes back with just enough force to maintain stability. Now, here is a fascinating point. The Sun does not possess a solid surface like a planet. If you could somehow stand on it, though you would be instantly vaporized, you wouldn't be standing on anything solid. You would simply sink inward. So, why doesn't the Sun's gas simply fall to the center? Because that delicate equilibrium between outward pressure and inward gravitational pull remains constant. It's like a tug-of-war where neither side ever gains the upper hand, at least not for billions of years. Stars are not eternal. They consume their fuel. 6 billion years. Scientists predict it will continue for another 5 billion years until its core hydrogen is exhausted. When that happens, the balance is disrupted. Gravity begins to win, forcing the star to contract until new fusion processes ignite. Helium starts fusing into carbon, carbon into even heavier elements, and the star expands into a red giant. Eventually, even these reactions cease, and that's when the story takes a dramatic turn. This is the phase where stars leave behind remnants, and these remnants are crucial to understanding why scientists began to wonder what comes next. If fusion cannot provide outward pressure indefinitely, what stops the star from collapsing entirely? This is where quantum mechanics enters the narrative. In a smaller star, once fusion ends, the collapse halts due to a phenomenon known as electron degeneracy pressure. This is a purely quantum effect that prevents electrons from being forced too close together. This strange but powerful force is a direct result of the Pauli exclusion principle, which states that no two electrons can exist in the same quantum state. When the star's core contracts, this invisible quantum rule resists gravity, establishing a fragile balance. This process gives us white dwarfs, incredibly dense stellar cinders no larger than Earth, yet containing the mass of a sun. If the star is more massive, that quantum resistance fails, and the collapse continues until neutron degeneracy pressure takes over, resulting in neutron stars. Here, gravity is so intense that protons and electrons are squeezed together, forming neutrons. The result is a sphere the size of a city with almost unimaginable density, where a single teaspoon of its material would weigh billions of tons. Neutron stars can also generate immense magnetic fields and spin at incredible speeds, becoming pulsars that emit radiation like cosmic beacons. And if the star is sufficiently massive, not even neutron degeneracy pressure can hold out. Gravity triumphs completely, and the star is believed to collapse into a black hole. In this final stage, all known forms of pressure fail, and spacetime itself curves inward with no way out. A singularity forms, hidden behind an event horizon, a point of no return beyond which light and information are lost forever. Black holes are not just cosmic tombs. They are engines of mystery, shaping galaxies and challenging our understanding of physics at its most fundamental level. This sequence, fusion, balance, collapse, remnant, is the conventional story. But when physicists delved deeper into the mathematics and pushed theoretical boundaries, they realized something profound. Perhaps black holes are not the only possible outcome. Maybe new types of pressure or entirely new states of matter could support stars in ways we have not yet witnessed. And that is where the concept of exotic stars emerged. So, what truly occurs when a star exhausts its fuel? That is where the tale grows darker. When a small or medium-sized star, like our Sun, finally burns through all its hydrogen and helium, it lacks the mass to undergo a catastrophic collapse. Instead, it shrinks into a white dwarf. At this point, fusion has stopped entirely. No new energy is generated in the core. However, there is a critical limit. White dwarfs cannot be infinitely heavy. In a landmark discovery, the Indian astrophysicist Subramanian Chandrasekhar determined this in the 1930s. 4 times that of our Sun. Beyond this point, the quantum-based electron degeneracy pressure, which supports the star by keeping electrons apart, simply gives way under the overwhelming gravitational force. This crucial boundary, now known universally as the Chandrasekhar limit, is a cosmic dividing line between stability and collapse, and one of the most significant insights in astrophysics. So, what happens if a star's core is more massive than that limit? Then the collapse does not stop. Gravity compresses the matter so intensely that electrons and protons combine into neutrons, and suddenly a new form of quantum resistance emerges: neutron degeneracy pressure. This leads to the formation of neutron stars, which are even more extreme. Picture squeezing the mass of our Sun into a sphere only about 20 kilometers across, smaller than many metropolitan areas. On their surfaces, gravity is so powerful it distorts spacetime itself. Their magnetic fields can be trillions of times stronger than anything we can generate on Earth. Still, neutron stars have their own breaking point. 2 solar masses, even neutron degeneracy pressure fails. Gravity overpowers everything. At that stage, according to established physics, no known force remains to halt the collapse. The star contracts beyond imagination, forming a black hole. From the outside, all you would observe is an event horizon, a boundary from which nothing can return. Inside, our known laws of physics cease to function. The mathematics suggests a singularity of infinite density, a point where the rules of nature no longer apply. And that is where the problem originates. Physicists are uneasy with infinities. They often indicate that our equations are incomplete, that something is missing from the theory. So, even though black holes are a widely accepted concept, the singularity at their core is a major concern. If our best physics predicts a breakdown, perhaps we have not yet uncovered the complete picture. Maybe there is another possibility, a different finale for massive stars that does not involve a singularity at all. That is when the discussion shifted from what occurs after fusion to a more fundamental question. Are black holes truly the only option? It is this line of inquiry that opened the door for exotic concepts like Gravastars and now even Nestars. On paper, black holes seem logical. A star depletes its fuel, collapses under gravity, and if it is heavy enough, nothing stops that collapse. The result is a region of space where gravity is so intense that even light cannot escape. Simple enough, right? But when you examine them more closely, complications arise. The first issue is the event horizon itself. From the outside, it appears to be a one-way passage. Cross it, and you are gone forever. But what does that actually imply for physics? If nothing can escape, not even light, does information itself get erased when it falls in? This conflicts with a core principle of physics. Information is not supposed to simply disappear. This conflict is what led to the famous black hole information paradox. Then there is the larger issue, the singularity. According to general relativity, if enough mass is compressed with nothing to counteract it, it collapses into a single point of infinite density. But infinities are not real answers. They are more like placeholders for our ignorance. A singularity indicates that we do not actually understand what is happening. It is akin to asking a calculator to divide by zero. You get an error, not a valid solution. Physicists are not comfortable with that. If singularities are real, it would mean the laws of physics have limits, places where they simply stop working. And that does not feel right. The universe should not have exceptions where mathematics simply fails. So naturally, the question arises, is a singularity the only possible end for a star, or is there another path, one we simply have not observed yet? This is where the situation becomes complex. Astronomers observe the sky and see incredibly compact, massive objects behaving precisely as black holes are predicted to. They bend light, warp spacetime, and in collisions, they produce gravitational waves that align with black hole models. From the outside, everything seems to fit, but the interior, the part concealed by the event horizon, is where the mysteries reside. We cannot observe it directly, and that creates an opportunity for alternative theories. If the inside of these objects is not a singularity, then perhaps black holes are not what we believe at all. Maybe they are being imitated by another type of star. A star constructed not from ordinary matter, but from exotic physics, something far stranger and potentially much more significant for our comprehension of the cosmos. That is the conceptual leap that led physicists to seriously consider exotic stars. Objects that resemble black holes, act like black holes, but are not black holes. If black holes leave us with more questions than answers, what could possibly take their place? That is where physicists began to get inventive. In the pursuit of understanding the limits of stellar compactness, an Austrian physicist named Hans Adolf Buchdahl made a pivotal contribution in the mid-20th century. Through detailed calculations within the framework of general relativity, he established critical limits on how small a star made of conventional matter could become. He demonstrated that no matter how clever nature's design, as long as a star consists of normal matter with positive energy density and positive pressure, Its size cannot shrink to exactly match the Schwarzschild radius, the critical boundary where a black hole of equivalent mass would form. In other words, even the most densely packed star imaginable must remain slightly larger than its corresponding Schwarzschild radius, hovering on the brink of collapse but restrained by the fundamental laws of physics. This might sound like a minor technicality, but it opened a massive door. If a real star can get almost as small as a black hole without actually becoming one, then perhaps there is room for different kinds of stellar objects to exist in that almost category. Physicists started asking, what if a star isn't composed of ordinary matter? What if its interior is governed by stranger rules? Negative pressure is particularly intriguing. Normally, pressure pushes outward, resisting collapse. But what if pressure could be negative in some regions, essentially pulling inward while other areas still push outward? That sounds unstable, but mathematically it can produce stable solutions where stars exist in equilibrium while being smaller and denser than anything observed. This is where it becomes challenging for astronomers. Imagine you are looking through a telescope and you see a compact object at the heart of a galaxy. Its gravity is extreme. It bends light. It consumes surrounding gas and emits energy. From the outside, it looks identical to a black hole. But what if it's not? What if it's an exotic star existing at the very edge of physics, mimicking a black hole so perfectly that it deceives nearly every observation we can conduct? This possibility has been a source of frustration for astrophysicists. Every time we detect something that behaves like a black hole, there is always that lingering doubt. Is it truly a black hole? Or could it be one of these exotic impostors? That uncertainty is part of what has driven the search for alternatives, ideas that challenge the black hole narrative without violating the laws of physics. And out of all those exotic ideas, one stood out. A model that not only replaces the black hole but also connects to one of the greatest enigmas in cosmology, dark energy. This is where the concept of the Gravastar, or gravitational vacuum star, enters the scene. The idea of a Gravastar sounds like science fiction, but it emerges directly from equations we already use to describe stars. In the 1930s, physicists Richard Tolman, J. Robert Oppenheimer, and George Volkoff developed what is now called the TOV equation. It is essentially a set of rules describing how pressure changes as you move outward from a star's center. Normally, this works well for ordinary stars. Pressure decreases smoothly until you reach the surface. But if you allow for the possibility of negative pressure at the center, the mathematics takes an unusual turn. Instead of a smooth gradient, the equations can yield exotic solutions where pressure behaves strangely, driven by negative values at the core. In early explorations, some models suggested extreme pressure variations, but these were mathematical oddities rather than physical realities. With carefully chosen conditions, such as an equation of state linked to vacuum energy, the math stabilizes into a remarkable solution. That solution is a Gravastar, short for gravitational vacuum star. Inside a Gravastar, you do not find ordinary matter like gas or plasma. Instead, you encounter something far stranger, vacuum energy. This is the same substance associated with dark energy, the mysterious force causing the universe's expansion to accelerate. Vacuum energy is peculiar because it has a constant positive energy density, but a negative pressure of equal magnitude. This negative pressure functions as a repulsive force, counteracting gravitational collapse. The interplay between positive energy density and negative pressure creates a delicate balance, preventing the star from collapsing into a singularity or expanding without control. This equilibrium does not eliminate gravitational effects but maintains a stable, compact object without an event horizon. Unlike a black hole, gravastars remain theoretical, yet they offer a glimpse into how extreme physics can reshape our understanding of stellar objects. What would it be like to be inside a gravastar? Surprisingly, not frightening at all, because the positive energy and negative pressure cancel each other out exactly. You would not feel pulled inward or pushed outward. In fact, you would float freely as if you were in empty space. It would be like being inside a bubble of pure vacuum, suspended in the cosmos. From the outside, however, gravastars would be almost identical to black holes. They would be so compact that their surfaces would lie just above the Schwarzschild radius, making them appear almost exactly like a black hole's event horizon. Light would bend around them, time would slow down nearby, and their overall gravitational behavior would mimic a black hole so closely that most of our instruments could not distinguish between them. This is why gravastars present such a challenge for astrophysicists. When we claim to have discovered a black hole at a galaxy's center, technically, we cannot eliminate the possibility that it is actually a gravastar. And here is the crucial part. Because gravastars are composed of vacuum energy, they are not merely black hole lookalikes. They could be linked to one of the most fundamental mysteries in cosmology: what dark energy truly is. That is the aspect that makes gravastars so exciting. If these exotic stars exist, they would not only resolve the singularity problem of black holes, they could also directly connect to the reason our entire universe is accelerating outward. And that is not just an alternative ending for stars. It is a new way of thinking about the universe itself. For years, gravastars were mostly regarded as an interesting theory, fun to ponder but unlikely to be real. That perspective is changing. In just the last few years, new studies have given the idea surprising substance. One of the most daring proposals is the concept of Nestars. In 2025, researchers from Goethe University in Frankfurt, including Luciano Rezala, demonstrated that Einstein's equations permit gravastars to be layered inside one another, like Russian dolls. Instead of a single exotic star, you could theoretically have multiple shells nested within the same object. This adds a new layer of complexity to what was once a relatively simple idea. Another line of research has focused on anisotropic gravastars, where the internal pressure does not behave uniformly in all directions. These models forecast slightly different light patterns when matter orbits them. The difference is subtle, but it means future high-resolution telescopes, like upgraded versions of the Event Horizon Telescope, might be able to differentiate them from black holes by examining the fine details of their shadows and light rings. Physicists are also investigating quantum corrections. A 2024 paper by Italo Pereira and Fokker Kyprianou suggested that gravastars could carry tiny quantum signatures in the way they bend light or shape photon spheres. These effects would be extremely faint, but in principle they could leave a distinctive mark. Finally, some researchers are constructing gravastar models within the framework of massive gravity theories. Unlike earlier versions that required exotic matter, these new models avoid singularities and event horizons while still adhering to the standard energy conditions of physics. That makes them more difficult to dismiss as mere mathematical curiosities. Collectively, These developments are shifting gravastars from fringe speculation to serious contenders. The challenge is no longer whether gravastars could exist, but how to prove they do. If gravastars and black holes appear almost identical theoretically, the crucial question is, how do we actually distinguish them in the real universe? That is where observations become vital. The first major tool at our disposal is gravitational waves. When two massive objects collide, like neutron stars or black holes, they send ripples through spacetime that we can now detect with observatories such as LIGO, Virgo, and KAGRA. Black holes have very specific gravitational wave signatures. The final moments of their merger, known as the ring-down phase, follow a predictable pattern. But if the merging objects were gravastars instead, some models predict the signal would not fade away smoothly. Instead, we might detect echoes, small aftershocks of gravitational waves caused by the fact that gravastars lack a true event horizon. It is like clapping in an empty room versus clapping in a room with walls that produce an echo. Detecting such echoes would be a strong indication that we are observing something other than a black hole. The second method to search for differences is through direct imaging. In recent years, the Event Horizon Telescope has provided the first-ever images of black hole shadows, like the famous one at the center of galaxy MADI-7. These shadows are formed by light bending around the object's intense gravity. Gravastars, especially anisotropic ones, would bend light in nearly the same way, but the fine details could vary, such as the thickness or brightness of the photon rings. The difficulty is resolution. Currently, our telescopes are adequate to spot the shadows, but not precise enough to notice those subtle distinctions. As technology advances, however, those details might become visible. There is also the matter of light and matter behavior near the surface. A black hole's event horizon allows nothing to escape, not even information. But a gravastar, lacking a true horizon, might permit tiny amounts of radiation to leak out. That means, in theory, accretion disks, the glowing matter spiraling into these objects, could shine differently depending on whether they are feeding a black hole or a gravastar. The effect would be minimal, but again, it is something astronomers are monitoring. Finally, there is the precision of mathematical modeling. For some compact objects, physicists have already calculated their radius with incredible accuracy, down to many decimal places, based on how they interact with their environment. So far, those measurements align almost perfectly with predictions for black holes, but almost is not the same as exact. If gravastars truly exist, their measurements would sit just a fraction above the Schwarzschild radius. It is a very fine line, and at present our instruments cannot make that distinction any finer. So for now, gravastars remain perfect impostors. They hide in plain sight, indistinguishable from the black holes we believe we understand. The only path forward is through more precise data, cleaner gravitational wave detections, and higher resolution images of these cosmic giants. Until then, every black hole we identify comes with an unspoken question mark. Or perhaps not. Black holes alone are mysterious enough, but gravastars raise the stakes by connecting directly to one of the biggest puzzles in modern cosmology: dark energy. Dark energy is the name we assign to whatever is causing the universe's expansion to accelerate. For the past 5 billion years or so, galaxies have not merely been drifting apart, they have been accelerating away from each other. The simplest explanation is that space itself possesses an intrinsic energy, something we call vacuum energy, which exerts a kind of negative pressure that pushes everything apart. That same vacuum energy is precisely what gravastars are hypothesized to be made of. This connection inspired a bold idea. Maybe what we call black holes are actually gravastars. In early 2023, a group of physicists led by Duncan Farah and Kevin Croker at the University of Hawaii published an analysis that brought this idea into the spotlight. They studied the growth of supermassive black holes in galaxies over cosmic time and noticed something peculiar. Their masses appear to increase at a rate consistent with a connection to dark energy. Their conclusion was audacious. Black holes might not have singularities at their centers at all. Instead, they could be more like gravastars, filled with vacuum energy and in the process contributing to the universe's dark energy budget. But the claim was contentious. Some astronomers expressed skepticism, arguing that the data might not have been interpreted correctly. Theorists contended that the growth of black holes and the expansion of the universe should not be directly linked in the manner the study proposed. The debate intensified because if the Hawaii team was correct, it would completely transform how we think about both black holes and dark energy. Suddenly, two of the greatest mysteries in astrophysics might be different faces of the same underlying phenomenon. Even with the criticism, the idea has persisted. Gravastars still offer a compelling bridge between the physics of collapsed stars and the destiny of the universe itself. If they exist, they would not only solve the singularity problem, they could also provide a physical explanation for why the cosmos is accelerating. That is why the possibility excites some scientists so much, even as others remain. So where does all this leave us? On one hand, black holes match almost everything we observe. They account for gravitational waves, align with images from the Event Horizon Telescope, and behave as Einstein's equations predict. On the other hand, the interior of a black hole, the singularity, remains a huge unanswered question. It is the part we cannot see, cannot test, and cannot fully explain. Gravastars step into that void. They imitate black holes from the outside but replace the singularity with vacuum energy on the inside. And if the latest theories are accurate, they might even come in nested layers or carry quantum signatures that leave minute traces in the surrounding universe. Instead of being dead ends in physics, they could be deeply connected to the very force shaping the cosmos, dark energy. The real challenge is that we are at the limit of our measurement capabilities. Our gravitational wave detectors are not yet sensitive enough to confidently identify echoes. Our telescopes cannot quite resolve the intricate details in light rings and shadows. For now, everything appears to be a black hole, but the question mark remains. Or maybe it doesn't. And that leads us to the ultimate question. If the universe is filled with objects that only mimic black holes, objects that are actually gravastars or even Nestars, what else might we be mistaken about regarding the cosmos? Could the force that drives galaxies apart already be residing at the very centers of galaxies themselves? In the end, it boils down to this. Either black holes are exactly what we believe them to be, or the universe has been concealing something far stranger right before our eyes. If you enjoyed this journey into cosmic mysteries, make sure to subscribe for more content that explores the wonders of the universe. Give this video a like if you found it fascinating, and share it with others who love exploring the frontiers of science.